It's intriguing to consider that dark energy might have actually facilitated the expansion of the universe instead of the contraction we assumed. For over 20 years, the prevailing framework in cosmology has provided a comprehensive narrative for understanding our universe. This framework, known as lambda cold dark matter or lambda CDM, intricately combines dark energy, dark matter, and the principles of Einstein's general relativity. It offers explanations for numerous phenomena, including the formation of galaxies, the expansion of space, and the characteristics of cosmic microwave background radiation. While this model has effectively unraveled many cosmic mysteries, the more we explore with advanced telescopes, the more complicated these explanations appear. Two notable discrepancies, referred to as the Hubble tension and sigma-8 tension, persist even in the face of substantial scientific advancement. Central to these challenges is dark energy, a perplexing component that constitutes almost 70% of our universe. The lambda CDM model posits that dark energy holds a static positive value, continuously propelling the acceleration of the cosmos. But what if this assumption is fundamentally flawed? What if dark energy once acted in a manner that countered the expansion before transitioning to its current role? A groundbreaking study has emerged, published in the journal Archive, suggesting just that. The researchers propose that vacuum energy, a concept related to dark energy, might have initially exerted an inward pull before changing course to drive the universe's observed expansion. Essentially, this implies that the universe may have shifted from a state of slowing down to one of acceleration. The shortcomings of the Standard Model. The most prominent inconsistency, known as the Hubble tension, involves measuring the current rate of the universe's expansion through observations of nearby galaxies and supernova. The findings yield a higher expansion rate than what is inferred from early universe data, specifically from cosmic microwave background radiation, indicating a significant discrepancy that cannot be simply attributed to measurement errors. The sigma-8 tension, though not as widely recognized, compounds this uncertainty. This aspect assesses how densely matter clusters across the cosmos. Certain galaxy surveys suggest less clumping than what the lambda CDM model predicts. Collectively, these discrepancies imply that our current understanding of dark energy and cosmic expansion might be overlooking crucial details, according to this innovative research. Dark energy's role may have undergone a significant transformation. The idea is that vacuum energy may have previously been characterized by a negative value, a force that subtly pulled space inward before shifting to positive and catalyzing the expansion we observe today. Diving into the details. In scientific terms, the universe might have transitioned from an anti-de Sitter phase to a de Sitter phase. If substantiated, this transition could potentially resolve both the Hubble and sigma-8 tensions. Prior studies hinted at this intriguing possibility, indicating that a sudden change in the sign of dark energy can lead to a harmonious fit across diverse datasets. This new investigation raises further questions. When did this transition occur? Did both phases exert the same influence on space, or was there a variation in curvature strength before and after the flip? Introducing this added complexity could either help clarify the model or create more confusion. The research approach. To delve into these inquiries, a team of researchers from the City University of New York employed a statistical method known as Markov chain Monte Carlo. This technique is adept at navigating expansive ranges of potential outcomes to identify those that best align with observational data. They utilize the Monty Python code in conjunction with the class Boltzmann solver to analyze a sudden change in vacuum energy. Their dataset was robust and varied, encompassing the 2018 Planck measurements of cosmic microwave background, meticulously chosen results pertaining to baryon acoustic oscillations, the Pantheon Plus supernova compilation, and weak lensing surveys from the KIDS 1000 program. These resources span from the universe's earliest visible moments to its recent structures. To ensure thoroughness, the researchers accounted for numerous nuisance parameters related to calibration and system specifics. Once they fine-tuned their models, they compared the effectiveness of each scenario against the observed data, being cautious to penalize unnecessary added complexity. So, key findings. The outcomes of this analysis brought both illumination and caution. The most straightforward iteration of the sign-switching model, where vacuum energy shifts but maintains consistent curvature, conformed well with the data. Not only did it correlate with the existing lambda CDM parameters, but it also alleviated both the Hubble and sigma-8 tensions. Conversely, when the curvature strength was allowed to vary between phases, the benefit of this added complexity diminished. Any improvements in fit were minimal and vanished under scrutiny for unnecessary complexity. In simpler terms, while the universe seems to favor a sign switch, it does not tolerate unnecessary complications. One particularly compelling insight was the relationship between the timing of the transition and the intensity of the prior negative vacuum energy. A stronger, earlier inward pull would necessitate an earlier transition to maintain the current expansion and clustering rates. Conversely, a gentler inward influence would allow for a later flip. This correlation was significant and generally independent of the 6 foundational CDM parameters. Understanding the physics. The concept of a cosmic phase transition may initially seem far-fetched, but it resonates with other familiar processes. Just as water can change states from liquid to gas, it's conceivable that vacuum energy might undergo similar transformations. Some theoretical frameworks even propose that the universe could tunnel between distinct vacuum states within quantum fields. Regardless, the effective description implies a sign flip at a certain redshift, a change that can be tested against observational data. The researchers diligently sought to avoid embedded assumptions in their interpretation. By opting for angular baryon acoustic oscillation data instead of comprehensive three-dimensional reconstructions, they minimized reliance on the lambda CDM framework itself. They also highlighted an essential mathematical nuance. While an instantaneous switch would introduce a sharp spike in certain equations, it would have minimal impact on the formation of cosmic structures like galaxies or clusters. Implications for cosmology. What does this mean for our understanding of the cosmos? Rather than claiming to unravel all mysteries surrounding dark energy, this study suggests that a relatively simple adjustment, a switch in sign without additional curvature alterations, can align with contemporary data while addressing long-standing tensions. It presents an elegant enhancement that preserves the successes of the lambda CDM model without forcing the universe into convoluted new pathways. Nonetheless, the proposal remains speculative. It lacks a recognized physical mechanism as grounding. The researchers themselves characterize it as a toy model, serving primarily to explore potentialities rather than confirming absolute truths. However, such models often ignite new avenues of thought, and this one hints at the possibility that the universe may have experienced a more dramatic narrative than previously conceived. Future observational surveys will provide critical tests for this hypothesis. Upcoming weak lensing studies and new measurements of baryon acoustic oscillations promise higher precision and fewer hidden assumptions. If the data continue to support the notion of sign-switching dark energy while dismissing added complexities, the case for this cosmic transformation will strengthen. Practical significance of the research, if validated, the idea of a sign switch in vacuum energy could fundamentally alter our comprehension of cosmic evolution. It may help resolve the most pressing issues faced in contemporary cosmology without dismantling the accomplishments of the lambda CDM model. For researchers and enthusiasts alike, this could lead to a clearer understanding of the universe's expansion dynamics, galaxy formation processes, and future cosmic developments. In a broader context, such research enhances human comprehension of our existence within this vast universe, and may even ignite new discussions about physics that extends beyond our current frameworks.